Imagine the vast expanse of the cosmos, teeming with billions upon billions of stars. Each star, a beacon of light, contributes to the grand tapestry of the universe. These stars are not scattered randomly. They cluster together, forming galaxies, nebulae, and other celestial structures. These clusters create the intricate and mesmerizing patterns we observe in the night sky. Just as astronomers seek to understand the universe by studying these cosmic groupings, data scientists use clustering to uncover hidden patterns and structures within data. This process is akin to mapping the stars, but instead, we map data points. Clustering is a powerful technique in machine learning that allows us to group similar objects together based on their characteristics. By analyzing these groupings, we can make sense of complex data sets and draw meaningful conclusions. It's like sorting stars into constellations based on their proximity and brightness. Each constellation tells a story, just as each cluster of data reveals a unique narrative. By identifying these natural groupings, we gain valuable insights into the underlying structure of our data. This understanding can lead to breakthroughs in various fields, from science to business. These insights have far-reaching applications in various fields. In marketing, healthcare, astronomy, and beyond, clustering helps us make informed decisions and predictions. In astronomy, clustering helps identify new galaxies and understand the evolution of the universe. By studying these groupings, astronomers can trace the history and future of cosmic structures. In marketing, it enables businesses to segment customers based on their purchasing behavior, leading to more targeted advertising campaigns. This segmentation allows companies to tailor their strategies to meet the specific needs of different customer groups. And in healthcare, clustering can assist in diagnosing diseases by grouping patients with similar symptoms. This can lead to more accurate diagnoses and personalized treatment plans, ultimately improving patient outcomes. Just as the cosmos holds countless secrets waiting to be discovered, data clustering offers a powerful lens through which we can unveil hidden patterns and unlock a deeper understanding of the world around us. By harnessing the power of clustering, we can navigate the complexities of data and uncover the stories it holds, much like astronomers charting the stars. One of the most popular and widely used clustering algorithms in the realm of data science is K-means. This algorithm is a cornerstone in the field, known for its simplicity and efficiency in grouping data points into clusters. Imagine a cosmic ballet where stars represent data points, and our goal is to group them into K distinct clusters, like constellations in the night sky. Each star or data point has its own unique position, and our task is to find the patterns that connect them. The K-means algorithm works iteratively, performing a celestial dance of data points until it finds the optimal cluster assignments. This iterative process ensures that the clusters formed are as accurate and meaningful as possible. The process begins with initialization, where we randomly select K initial cluster centers, like choosing K random stars as our starting points. These initial centers are crucial as they set the stage for the entire clustering process. Next comes the assignment step. Each data point, or star, is assigned to the nearest cluster center based on its distance, just as stars are drawn to the gravitational pull of their nearest celestial neighbor. This step ensures that each data point is grouped with others that are most similar to it. This process is repeated for all data points, effectively grouping them into K initial clusters. These initial clusters are just the beginning, as the algorithm will refine them in subsequent steps. Once all data points have been assigned, we update the position of each cluster center by calculating the mean of all data points belonging to that cluster. This step is akin to finding the average position of all stars in a constellation. This is like finding the center of gravity for each constellation. By recalculating the center, we ensure that the cluster center is as representative as possible of the data points within it. The assignment and update steps are repeated iteratively, with data points shifting allegiances between clusters and cluster centers, adjusting their positions accordingly. This iterative process continues until the clusters stabilize. This cosmic dance continues until the cluster assignments no longer change significantly, indicating that we have reached a stable solution. At this point, the data points have found their rightful place in the universe of clusters. The final result is a set of K clusters, each representing a group of data points that are more similar to each other than to those in other clusters. These clusters reveal the hidden structure within the data, much like constellations reveal patterns in the night sky. This provides a powerful way to visualize and understand the underlying structure of our data. By grouping data points into clusters, we can uncover insights and patterns that might otherwise remain hidden, allowing us to make more informed decisions based on our data. K-means clustering is a versatile algorithm, but like any tool, it's essential to understand its strengths and limitations. This understanding allows us to apply it effectively and avoid common pitfalls. Imagine trying to use a telescope to observe a distant galaxy. The telescope's capabilities and the clarity of the night sky will influence the quality of our observations. Similarly, the effectiveness of K-means depends on the nature of the data and the context in which it is used. K-means shines brightest when dealing with datasets where clusters are spherical and have similar sizes. These clusters are like well-defined groups that are easy to identify and separate. Think of these as well-defined constellations with a clear center and a relatively even distribution of stars. In such scenarios, K-means can quickly and accurately group data points into distinct clusters, making it a powerful tool for data analysis. In such cases, K-means can efficiently group data points into distinct clusters. This efficiency is particularly useful in fields like market segmentation, where businesses need to identify distinct customer groups. However, K-means may struggle when dealing with datasets containing clusters of varying shapes, sizes, or densities. These irregularities can confuse the algorithm, leading to inaccurate clustering results. Imagine trying to group stars into constellations when some are clustered in tight groups, while others are scattered sparsely across the night sky. This scenario illustrates the challenges K-means faces with non-spherical clusters. In such cases, K-means may struggle to accurately identify the underlying structure. This limitation can be particularly problematic in fields like biology, where data often forms complex, non-spherical patterns. Another important consideration is the choice of K, the number of clusters. Selecting the right number of clusters is crucial for the success of the algorithm. Choosing the right K is crucial, as it directly impacts the quality of our clustering. Too few clusters can oversimplify the data, while too many can overcomplicate it. It's like deciding how many constellations to divide the night sky into. The right balance is essential to capture the true structure of the data without introducing noise. Too few, and we miss important details. This can lead to a loss of valuable information and insights. Too many, and we create artificial divisions. This can make the data harder to interpret and reduce the clarity of the results. Despite its limitations, K-means remains a valuable tool for exploring and understanding data. Its simplicity and efficiency make it a popular choice for many applications. By carefully considering the characteristics of our dataset and the choice of K, we can leverage the power of K-means to uncover hidden patterns and gain valuable insights. This thoughtful approach ensures that we make the most of this powerful algorithm, enhancing our ability to make data-driven decisions. To illustrate the power of K-means clustering, let's embark on a journey to explore the IRIS dataset, a classic dataset in the world of machine learning. Picture this dataset as a celestial tapestry woven with data points representing different species of iris flowers. The IRIS dataset contains measurements of sepal length, sepal width, petal length, and petal width for 150 iris flowers belonging to 3 different species: Setosa, Versicolor, and Virginica. Our goal is to use k-means clustering to group these flowers into clusters based on their measurements, effectively identifying the different species. Imagine each data point as a star in our cosmic tapestry, with its coordinates determined by its sepal and petal measurements. By applying k-means clustering with k equals 3, we aim to group these stars into 3 distinct constellations, each representing a different iris species. As the k-means algorithm dances through the data, assigning stars to constellations and adjusting their centers, we begin to see the emergence of 3 distinct clusters. These clusters, like celestial patterns, reveal the underlying structure of the iris dataset, separating the iris flowers into their respective species based on their unique characteristics.